Okay, introduce our speaker, Bhuwan Dhingra. He is a PhD candidate from SMU, and he's advised by William Cohen and Ruslan Sakakudinov. And his research interests is natural language processing, machine learning, and knowledge base and human control. So, and I'm very happy to have him come to introduce his work, his thesis work. And let's welcome our speaker.
Thank you, Nanyuns, and thanks a lot for attending my talk today. So today I'm going to talk about a very old problem in AI, which is how do we represent knowledge about the world such that we can compute with it? And specifically, I'm going to discuss methods for injecting world knowledge into end-to-end learning. So what do I mean by end-to-end learning? Really, what I mean is a system which looks something like this. You have an input, which passes through the many layers of a deep neural network to produce an output. So the input might be an image and the output might be a label for the object in that image. Or the input might be a sentence in English and the output might be a sentence, the same sentence in French. But for many complex tasks in AI, we actually just inputs and outputs are not enough. So let's say I want to build a health-related question answering system to answer questions like these. Now in this case, the answer to the question depends not only on the input here, but also on a much broader knowledge about medicine and biology. And this knowledge can appear in many, many different formats. So some of it might be written down in news articles or scientific publications. Some of it might be organized in medical ontologies. And a lot of it might be just loosely structured in tables and lists spread out across the web. And this sort of general framework goes beyond just question answering. There are many, many tasks that we are interested in where we want to make a prediction based on some background knowledge about the domain in which that prediction needs to be made. And if you want to apply machine learning to any of these tasks, we need to figure out how to represent knowledge about that domain and build learning algorithms which can reason with that knowledge. That's exactly the goal of my research, to develop a general framework for injecting domain knowledge into end-to-end machine learning. And there are some very important challenges here. So first of all, I've already mentioned that domain knowledge can appear in many, many different formats. Some of it can be in text or ontologies or tables, whereas most of the machine learning methods that are developed today are really specific to a single kind of data, either text or graphs or images. Often the information that we want to use is not written down nicely in one place, but it needs to be aggregated from multiple sources. For example, if I ask you how much population has potentially been affected by the coronavirus, you'll first try to figure out, okay, where have I seen cases of coronavirus, and then go somewhere else and find the populations of all those places, and then maybe sum them up. So this is called reasoning, which in this talk I'm going to take the definition of reasoning as just aggregating information from multiple sources to derive new information. Lastly, often in a practical setting, all we have to do a task is a training data set which consists of input and output pairs. We don't really always exactly know what is the piece of knowledge that we need to map a specific input to a specific output. And this makes the learning problem much more challenging, because now given an input, we first need to search what could be a potentially very large source of knowledge for the relevant information needed to map that particular input to an output. And obviously this makes the learning problem harder. Now, during my PhD, I've worked on various issues related to those three challenges that I talked about. But today, I'm going to focus mostly on my work on factoid question answering, which I believe captures all those aspects nicely. The setup is simple here. We have a natural language question as the input, and we want to produce a natural language answer as the output. And I'm going to assume we have some access to both structured and unstructured knowledge about the domain in which the question lies. And the term factoid here simply means that our questions are about facts or about information which is unambiguously true or false given the underlying domain. And in practice, what this means is that I'm going to assume that our answer or set of answers for a question are unique, short, and unambiguous. Now, this is a very big assumption. In general, natural questions that people have don't always have unambiguous answers. There's sometimes uncertainty, questions are up for interpretation, and there are confidences associated. But I'm going to sidestep those issues and assume that, okay, the questions that we are interested in admit factual answers. So before I go into the details, let me give you an overview of the outline for today. So I'm going to start by addressing how we can answer factoid questions using text corpora as our source of knowledge. But then I'm going to highlight some limitations of that approach and how we can address those limitations using a combination of text with knowledge graphs. And then lastly, I'm going to discuss how we can make these methods entirely end-to-end, which I'll describe what I mean by. Then towards the end of the talk, I'll briefly outline some of the other work that I've done during my PhD, and in the end, I'll lay out some directions for future work. So let's start with using text as a knowledge source for answering questions. So in some sense, this is the most natural setting. People share information in natural language. So if you take any domain like biology, medicine, or news, most of the information in that domain is actually written down in natural language and can be found in large text corpora. So to answer a question against a text corpus, we can proceed in two steps. First, we can run a text retrieval method to identify a small passage or a set of passages which are highly likely to contain the answer to the question that we're interested in. And this process needs to be fast. We need to compare the question to maybe millions of passages. So usually this is done using some shallow method like matching the keywords in the question to keywords in the passages in our corpus. Then once we have these relevant passage or set of passages, we can run a more complex model for extracting the exact answer to our question, which is also known in the literature as the task of reading comprehension. And here I'm going to assume that the answer that we are looking for is a span of text within the passages. So essentially, this task of extracting a span of text as an answer to a question is one of span classification. So if I list out all the different spans which appear in my passage, I want to identify the one span whose meaning in that context, based on the information around it, matches what is requested by the question. And the way I'm going to do that is by defining a scoring function. The scoring function is going to take in the question as an input and the span as an input. And it's going to try to score spans which are answers to the questions high, whereas the spans which are not answers to the question is going to try to assign them a low score. So to do this, we can use what is now a pretty standard architecture, which is we'll represent each of our spans as a fixed size vector, which we are going to derive using a recurrent neural network applied to the input passage. Similarly, we are going to create a fixed size vector for our question, which is going to come from another recurrent neural network. And then we are going to model the score between a question and a span as the inner product between these two. And now we're going to assume that we have access to some training data which pairs questions with their answers to train the parameters of the two recurrent neural networks. Now, this basic model works, this already works much better than handcrafted approaches which try to derive a meaning representation from the question and meaning representations from the passage, but we can make this a lot better. And much of the early work that I did during my PhD was in adding some inductive biases based on our understanding of this problem to improve this task. So one thing that we can do is we can, instead of representing the spans independently of the question, we can inject some information from the question itself into the recurrent neural network, which represents those spans, to build what are called query-dependent representations. Yet another bias that works well here is, so during training, there may be certain rare words in our passages. And in this case, what we can do is, instead of modeling their representations independently, we can model them as a composition of the different characters in those words. So for example, here, alpha-glucosidase, the meaning of that has something to do with its constituents. And this really helps in building better representations of some rare terms and concepts in a domain. Lastly, notice that essentially we want to learn span representations here, but often the information that we want about a span may not be in a very local context around that span. It may be pretty far away in the passage. And this happens a lot when there is co-reference in the document. So here we have the chemical Vogel-Bose, but there is more information about it further away using the co-referent mention it. So to deal with these sort of phenomena, we introduced a co-reference aware recurrent neural network, which aggregates the information around all the different mentions of the same concept to build better span representations. Now, over the years, I have applied these models to many, many different tasks and many data sets for language understanding. And, in some cases, we had state-of-the-art. In some cases, we were close. In most cases, these are now replaced with bigger, better models. But today, what I really want to focus on are some of the limitations of this purely text-based approach of answering questions. So in particular, I'm going to focus on two limitations. So first of all, note that implicitly what we are trying to do here is we are mapping the question to an open class of textual patterns to find out, okay, which is the span which answers this question. But natural language is pretty diverse. So in general, whatever function we train here for matching questions to spans turns out to be pretty brittle in practice. And what do I mean by that? So for example, one sort of brittleness that we see even in state-of-the-art models today is that adding some distractor text, which is related to the question but doesn't actually answer it, can often flip the prediction to an incorrect one. So in this case, the model is not able to understand negation. The other limitation, which is in some sense more fundamental, is the inability to deal with complex multi-hop questions for this pipeline. So a multi-hop question is one where we're looking to aggregate information from multiple passages. So let's say I want to answer the question, what are the side effects of diabetes treatments? To answer this, we want to first answer the sub-question that, okay, what are the treatments for diabetes? And then we want to answer what are the side effects of those treatments? And this information might be in very different passages in our text corpus. So in this case, what happens is that step one over there, which retrieves the relevant passages given a question, may not retrieve all the relevant passages, because to get the passage which answers the second sub-question here, we need to answer the first sub-question. So in general, that pipeline of retrieving text and reading does poorly on these kind of complex questions. Now, these problems are not new. People have thought about them a lot. And traditionally, how they address these problems was using a more structured format for representing information. And that's what I'm going to discuss next. So in particular, I'm going to focus on knowledge graphs, or which are more commonly known as simply knowledge bases in the literature. So the idea here is simple. You start with some unstructured collection of text, and you start by first identifying all the important concepts in your text that you care about. And these are also called as entities. And you're going to create a node for each entity that you detected in your knowledge base. Now, the important thing to note here is that there is a process of normalization over here. So while diabetes in the knowledge base will have a single node, it may have many, many different mentions in the text corpus. And we are going to normalize all those mentions to a single node over here. Then the second thing you can do is you can go over your text and you can identify the relations between pairs of entities as expressed in your text. And these become edges in your knowledge base. And once again, there is a process of normalization going on over here. While the relation that diabetes has an effect of peripheral neuropathy might be expressed in many, many different ways in your text corpus, in the knowledge base, we are going to assign a fixed type from a predefined vocabulary. And even for the largest knowledge bases, this vocabulary is at most a few thousand different types of relations. So now we have a more structured format for the information there. And notice now that this knowledge base actually does address some of the limitations that I talked about earlier. So instead of dealing with an open domain, an open class of textual patterns to answer your questions, you're now dealing with a closed set of entities and relations that you want to match your question to. Also, as I said, there is a normalization. So we know for sure that all the information about diabetes is in a small neighborhood in our knowledge base. So this helps in doing multi-hop reasoning or identifying paths of relations in the knowledge base which answer more complex questions. And in fact, there's been a lot of work on using knowledge bases for all sorts of tasks. And most of those approaches actually throw away the text and completely ignore that. But from the perspective of the kind of knowledge that we're talking about, actually most of the information is lost going from text to knowledge base. While there is a rich open domain of rich information in our text corpus, here we really only have a shadow of what we started with. So, and also it's slow and error prone to actually convert the text into a structured format like this. So the question is, can we use both of these sources together to answer questions? And that's what I'm going to talk about in the next few slides. Yeah.
Do you always assume that the knowledge base is extracted from text? I mean, in biology,
no.
They have lots of knowledge base.
Yeah. So this can come from images, this can come from semi-structured tables and this. I'm going to assume that the domain that we're interested in, we already have a knowledge base. And this is my starting point. Yeah.
How do you address noise? Or do these edges have some probabilities associated with them? Or
so you mean noise in this side?
In the when you extract a relation, there might be multiple sources, even contradicting each other.
Yeah. So I'm not going to address that issue here. That's a very important issue in constructing unstructured data to a structured format. But I'm going to assume that the knowledge base we have is high precision. So you're going to ignore any relation which you're not confident about and only populate those relations which you're extremely confident about. And that's one reason why these things are are very sparse. Most of the information is not here because you only keep the very confident facts. Whereas here you have all sorts of information and maybe sometimes even conflicting information. But yeah, suppose we start here. The question now is, how can we use both these sources to do a task that we're interested in this case, question answering? There has been some prior work, not as much as the one which looks only at text or only at knowledge bases, but there has been prior work on using both. So for example, but there are some limitations. So for example, open vocabulary semantic parsing, the basic idea behind there is that given a question, you will first write some rules to parse that question into a logical form, and then execute each step of the logical form against text or knowledge base. Or there has been work on universal schema, which takes both your text and the knowledge base and maybe some other sources and embeds them into a shared dense vector space. But in doing so, it actually ignores the rich graph structure we have in the knowledge base here, which has some limitations, which I'm going to talk about. So instead, the approach that I'm going to talk about assumes that we have access to entity linking, which is the process of connecting a concept in my knowledge base to all the different mentions of that concept in the text corpus. And once again, entity linking is a very difficult, complex task in itself. But here I'm going to assume that we have access to an off-the-shelf tool which does this for us. And this can be noisy. So once we do run entity linking and we get this combined data structure consisting of both text and knowledge bases, now there are some benefits to using this combined data structure. And specifically note that now, if I build a model for reading text, because there are these connections to the knowledge base, I have access to rich background knowledge about the concepts that I encounter in text. Flipping this around, now if I'm reasoning over the knowledge base, I have access to a much larger set of paths connecting the concepts in my knowledge base. And in some sense, the text on the left completes the missing information in the knowledge base on the right. So how can we build a model which represents both these sources jointly? So the approach that I'm going to take here is going to be very analogous to the approach that I described for answering questions again text. We're again going to have two steps. So the first step is going to be a retrieval step. So in general, the kind of corpora and knowledge bases we will consider can be very large. So instead, we'll start with, once again, with a retrieval step, and now we're going to augment it with an entity linking step for identifying the important entities mentioned in the question. And using that, we're going to extract a small subgraph, which would be, say, 50 passages and 500 entities, which is relevant to the question and is likely to contain the answer to our question. Now, given this subgraph, next we're going to run a graph comprehension step now instead of a reading comprehension step for identifying the answer within this subgraph for the question. And now I'm going to assume that my answer is an entity instead of a span. So how can we do the second step of graph comprehension? So let me take a simple example. Let's say I have a question, who voices the dog in Family Guy? And my subgraph contains the node Family Guy, which is a TV show, the dog character in that show, Brian Griffin, and the voice actor who voiced that dog. Now, answering a question like that against this subgraph is essentially a process of identifying a path, which starts at the entity mentioned in the question, Family Guy, and follows as a sequence of relations to arrive at the answer. And note that we need to use the text here because a relationship like includes dog may not be there in our knowledge base. So again, to do this task, I'm going to use an approach which is going to be very similar to the kind of approach I described for extracting answers from text. I'm once again going to define a scoring function between my question and each of the entities in my knowledge base. And again, the question representation is going to come from a recurrent neural network applying the.
So you're assuming your knowledge base that it doesn't know that the character is a dog?
Yeah. Yeah. So in this case, I'm assuming that the knowledge base admits a type which has character, but does not admit a type has a dog character.
But it doesn't have a has type dog, instance of dog.
Yeah, I'm assuming that's not there.
Okay.
So the question, again, we're going to represent using a recurrent neural network. But now for the entities, note that when I wanted to classify spans, the representation of a span depending on the context in the text around that span. Now for an entity, instead, we want to represent that entity based on the paths in the graph which exist around that entity. And for that, I'm going to use a graph neural network, which is the general technique for embedding the nodes in a graph based on the neighborhood around those nodes. But in order to apply graph networks to our problem, we developed a slightly different variant of graph networks, where the representation of a node depends on both its neighbors, its entity neighbors in the graph, as well as the mentions of that node in the text sentences that we have in the graph. And using this process, we can learn representations and define the scoring function. And once again, given training data, we can optimize that scoring function. Yeah.
I wonder what's the scale of this? Will you have any scalability issue?
Yeah, so as I said in the beginning, in general, the knowledge sources that we considered were all of Wikipedia and all of Freebase, which are massive. But we had a retrieval step at the beginning. So given the question, we first identify the terms in the question and passages which match those. And then we also identify the entity in the question, in this case, Family Guy, and we took a small neighborhood around that concept.
Okay, so usually for that subgraph, how large is it?
This was about 500 entities and 50 passages, okay, which is efficient to train. I'm going to address that in the last part of the talk. Yeah. So how does this do? We tried this on two pretty widely used question answering benchmarks. What I'm showing here is a performance in terms of hit set 1, or the accuracy of the topmost prediction, with varying levels of KB completeness. So by KB completeness, I just mean what fraction of the facts which are required to answer the questions are present in the knowledge base or not. And as you would expect, as you increase the knowledge base completion, a model which uses only the knowledge base gets better. And even with 50% of the KB, you can do much better than a model which uses the text alone, which sort of justifies the motivation that it's easier to answer questions against a knowledge base. What works best, though, is having both knowledge base and text using the graph network model that I just described. And what's encouraging to see here is that even with just 10% of the knowledge base, we can do much better than a text-only baseline by combining both knowledge bases and text. And in general, I talked about universal schema briefly as another approach which embeds these things. As you can see, that does poorly, and the main difference is that it doesn't consider the graph structure of the knowledge base when learning representations of the different facts within that. We can also check the performance for queries of different levels of complexity. So here on the x-axis, I have 1 hop, 2 hop, 3 hop questions, where the number of hops is the length of the path that you need to consider to answer a question. So 3 hop questions are more complex than 1 hop questions. And here we have mixed results. So if we check the performance using a complete knowledge base, which is the blue bar, then we see that it does pretty decently. And there is a small drop-off in performance, but overall it's decent. On the other hand, if you use an incomplete knowledge base with text, or if we just use text with our graph network model, then the performance drops off quite significantly for more complex questions. So what's going on here? And that's what I'm going to focus in the last part of my talk. Yeah.
So, could you, isn't it surprising that 3 hop performs for text, for instance, better than 2 hop?
Yeah, I mean, this is actually noise. There is certain noise in these questions. Some questions are labeled as 3 hop, but they're actually not 3 hop. Sometimes the answer is right there. So yeah, these are both really bad. Yeah.
So I have a general question, which is, are you assuming that the knowledge base is built from the text, or that the two are actually independent of each other and you've just linked them doing this entity linking?
Yeah, that's a great point, actually. So I'm not assuming whether it's built from the text. In general, it can come from a very different source from the text corpus I have. But the data sets that I considered, Wikipedia and Freebase, Freebase was in part constructed using Wikipedia. And there was also a lot of manual annotation and information from other sources. But yeah, the method that I'm describing is applicable in any case. Though the problem of entity linking becomes much easier if your knowledge base is actually constructed from the same source of text. So there was definitely less noise in entity linking here than there would be in some other domain.
Okay.
Yeah.
I'm sorry, I just wanted to also ask, do you have an intuition why the drop in 100% knowledge base is so much more drastic than for the knowledge base in text and just text, from 2 hop to 3 hop, I mean?
Yeah, that's a good question. Yeah, I don't have an answer to that. Yeah. But yeah, so as I said, there is a steep drop in performance if we don't have a complete knowledge base. And really the reason for that is that our model is not truly end-to-end. So this is the pipeline that I've presented so far, right? Given a question, we run retrieval to identify a small subgraph, and then we run a graph comprehension step. The problem still is that retrieval does poorly on multi-hop questions if our knowledge base is not complete. Because we go back to the same problem that given a question, we are not guaranteed to retrieve all the relevant passages and if there is no knowledge base connecting the information. So let me take a concrete example. Let's say I have a question, where is the company which manufactured Vogelibos headquartered? This is a 2-hop question. And for now, let's assume we just have a text corpus to answer this question. But the methods that I'm going to describe are applicable to a text plus KB setting as well. So I'm going to focus on a text-only setting. So implicitly answering that question requires 2 steps. So we need to answer these 2 sub-questions. Which company manufactured Vogelibos? Get the answer to that, and then find where is X headquartered. And the answers to these 2 questions can be in very different passages in our text corpus. And the problem is that to retrieve this second passage, we need the answer to the first question, which is why retrieval, directly retrieving passages based on my question and the corpus fails for these kind of questions. So also, I'm going to assume a practical setting where we don't know these intermediate steps. We don't know the decomposition of a question into these sub-questions. We don't know what passages are required to answer those sub-questions. So how can we build a model given just a data set of question and answer pairs to do this sort of reasoning? Now, there is, again, some prior work which has looked at this problem, and sort of the general theme of that work is, given the training data set of question and answer pairs, you use some heuristics to decompose the training questions into the intermediate steps. And then you train two models, one model for decomposing the question into the intermediate steps, and another model for answering each of those intermediate steps. Then during inference, given a test question, you apply both your models to first decompose that question and then iteratively answer each sub-question. So the problem here is that the heuristics that you use to decompose your question may not generalize beyond a particular data set for which they were constructed. And during inference, because you are running an expensive model for answering each sub-question iteratively, things can get quite slow. So instead, I'm going to try to answer the question whether we can do this end-to-end. So can we do this without relying on heuristics to find these intermediate sub-questions? Can we still do this efficiently against a very large text corpus, maybe all of Wikipedia? And by efficient, I mean in very fast runtime. And can we still maintain this nice compositional nature of answering the question in these two steps? So can we maintain this interpretability of first answering the first sub-question and then answering the second sub-question? So at the heart of the approach that I'm going to describe is what I call a relation following operation. And this operation is really motivated by how people use knowledge bases. And it looks up something like this. So given a starting set of entities X, we want to follow the relation R to arrive at an output set of entities Y such that every member of Y satisfies the relation R with some member of X. Now, suppose I have such operation implemented against my text corpus. Then to answer this question, I can now proceed in the following steps. I can identify a starting set of entities X, in this case, which is going to be just a singleton chemical Vogelibos. And then I'm going to derive two relations which I need to follow starting from that entity to arrive at the answer. So relation 1 is the manufacturer relation, and relation 2 is the headquarter relation. Once I derive these three things, I can apply my relation following operation twice in a compositional manner to arrive at the answer. Now the key thing that I'm going to describe, an implementation of this operation against the text corpus, and the key idea is that we can do this in a differentiable manner. So we can derive these things implicitly in a soft manner, apply our operation twice, and still be able to backpropagate all the gradients from the answer to the starting question. So train these three things in an end-to-end manner. So how can we go about implementing this operation? For a moment, let's imagine that we just have a symbolic knowledge base or a knowledge graph to do this. Now, there is a very simple way we can implement this against a graph like this. So we can represent our starting set of entities X as a sparse vector whose non-zero elements are going to correspond to the members of the set. The size of this sparse vector will be the total number of entities in our knowledge graph. Similarly, we can represent the relation R as a sparse adjacency matrix, whose size will be number of entities by the number of entities, and whose ijth element will be 1 if the relation R holds between entity I and entity j. So if we represent our relation and set of entities X in this manner, then the relation following operation is a simple sparse matrix times sparse vector product, which can be implemented very efficiently in time independent of the actual number of entities in our knowledge graph. But of course, we don't have a knowledge graph. Instead, we have a big text corpus. How can we do something like that on a text corpus? So once again, I'm going to assume that we have access to an entity linking system, which identifies all the important concepts in my text and normalizes them to these entity nodes on the right. So here we have entities on the right, and the same entity can have multiple mentions in my text corpus. So now once we have this augmented text corpus with entity information, the way we are going to go about implementing our relation following operation is going to be something like this. So suppose I'm starting with the set X, which is Family Guy, and I want to follow this relation, which can be described as dog in the show Family Guy. Now, the first step that we're going to do is we're going to expand the starting set of entities X to all their co-occurring mentions. So in this case, for example, let's say we have 3 co-occurring mentions with Family Guy. Second, we are going to filter those mentions based on whether they satisfy the relation that is being requested or not. In this case, whether there's a dog in the show. So as you can see, only the middle mention of Brian Griffin satisfies this. In practice, we're not going to do a hard filtering here, but we're going to define a scoring function between the context of a mention and the description of the relation that we are interested in. And then the last step is, because the same entity can have many different mentions in text, we're going to aggregate the scores of all the mentions of an entity to a final output, which is again at the entity level. And this is going to be the output set Y. Now, the key idea is that we can do all 3 of these steps very efficiently against a very large text corpus if we restrict our scoring function to be an inner product. So how do we do that? So let's start with step 1, expanding the set of entities X to their co-occurring mentions. So once again, I'm going to use a sparse representation of the set of entities. But now, instead of multiplying it with an adjacency matrix which describes a relation, I'm going to multiply it with an adjacency matrix which goes from entities to the mentions co-occurring with that entity. So the size of this is number of mentions in my corpus times the number of entities. And the output is going to be a sparse vector, the same as the number of mentions in my corpus, but whose non-zero elements are exactly the mentions which co-occur with my starting set of entities. And this matrix can be pre-computed. So the second step is we want to filter the mentions which co-occur with our starting set of entities based on whether they satisfy the relation R or not. So suppose I have a mention like this of Brian Griffin in a text sentence, and I want to filter it based on the relation of request. So the way we're going to do that is we're going to build a dense representation of the relation, and we're going to build a dense representation of the mention which encodes the context in which that mention appears. And then the scoring function is going to be an inner product between the representation of the relation and the representation of the mention that we derived. And in this case, we're going to use a transformer network, which is a standard model for encoding text sequences. Now, one of the interesting things here is that we can actually pre-train this transformer network on something like language modeling to produce contextual representations of different mentions. And because we can pre-train this, what we can do is, in an offline step, we can take all the different mentions in my text corpus and create an index of all their dense vector representations. So this whole thing can be done offline. So that at runtime, when we get a query, then identifying sort of the mentions which are related to that query is like a top k nearest neighbor search algorithm. So here I'm going to compare my query vector here to a pre-computed offline index and select the top k mentions which have the highest inner product score with my query. And the result of this operation is going to be another sparse vector, again the size of the number of mentions in my corpus, because that's what I populated in my index. And now it will have exactly k non-zero elements, where k is the parameter, the top mentions matching the relation based on inner product. So now I have 2 sparse vectors, right? From step 1, I have a sparse vector encoding all the mentions which co-occur with my starting set of entities. In step 2, I have a sparse vector whose type matches the relation that I'm requesting. And what I really want is an intersection of these two. So I want mentions which both co-occur with the starting set of entities and who satisfy the relation R. So we can do that using an element-wise product between these 2 sparse vectors, and we end up with another sparse vector which satisfy these, which are mentions which satisfy this x.follow R operation. And lastly, what we have is at the mention level, we want to aggregate scores of all the different mentions of the same entity. So what we're going to do is multiply it with another sparse matrix, which now encodes co-reference. So every row here are all the different mentions of the same entity. And at the output, we're going to get exactly the set of entities which satisfy x.follow R. So to summarize all those things in one equation, it looks something like this. So we start with the sparse vector representing the input set of entities, and we end up with the sparse vector representing the output set of entities. The three steps that we took was expand to co-occurring mentions, filter based on whether they satisfy the relation R, and then combine scores of the same entity to arrive at the output. Now, there are some nice properties of implementing this relation following operation in this manner. So first of all, this is very efficient. So every operation here is either a sparse matrix times sparse vector product, or it's a top k nearest neighbor search. And actually, the complexity that we get is independent of the number of mentions in our text corpus. Secondly, this is closed under composition. So what do I mean by that? We started with a sparse vector of entities, and applying our operation once resulted in another sparse vector of entities. So now I can chain these operations together. I can define something like X, follow R1, and then follow a second relation R2. And thirdly, very importantly, every operation here is differentiable. So what do I mean by that? The confidence, the weights of the entities in my output sparse vectors are differentiable with respect to the weights in the input, as well as this query, this relation vector that I have in the middle. Now, this is really important for doing multi-hop question answering. So let's go back to the figure I had earlier. How can we actually go from a question to an answer here? So what we're going to do is we're going to derive a sparse vector X using a soft entity linking system on our question. This can be some neural entity linking system. And then we're going to derive representations of the two relations which are requested by the question. And in this case, we use two transformer networks applied over the question to get R1 and R2. Once we have these three things, we're going to apply our relation following operation twice. And the cool thing is, because everything is differentiable, whatever loss we incur on the final answer can be backpropagated all the way through these three different networks. Are there questions? Yeah.
In practice, how brittle are the transformers that extract the relations from the question?
What do you mean by brittle?
For example, if you phrase the relation slightly differently, would it still produce the correct?
Yeah, so notice that nowhere am I explicitly relying on a relation. These are more at a conceptual level.
Okay.
This goes from a natural language question to a natural language answer. So it is brittle in the sense because your training data set is going to be limited.
Yeah.
There are going to be patterns that it never saw during training, and it's going to fail on those. And it is also going to be dependent on my pre-training objective for encoding all those mentions into a representation, right? So language modeling is, as a pre-training task, is good for capturing certain kinds of relations, but not all of them.
Yeah.
So it is brittle in that sense.
Okay.
But nowhere am I actually manually defining a list of relations that I care about. This is really an open class of relations that we're dealing with.
So you have been mentioned about that relation representation, but you didn't give any detail. Is it like just two transformers?
Yeah, so it's two transformers with some shared parameters, but at the end of the day, I assume I know it's a two-hop question. Mm-hmm. So I know there are two relations that I'm interested in. I know there is an order between them. There is a first relation and a second relation. And really, given a question, I'm just applying two trainable neural modules to derive those representations.
Okay, and you train them from scratch?
Yeah, so given just a data set of question and answer pairs, yeah.
Okay.
Yeah.
So how do you know it's a two-hop question?
So I'm going to assume that we know that, but obviously in most cases we won't know that. So one thing that we do in those cases is we actually apply three different networks. One has only one hop, the other has two hops, the third one has three hops. And now again, my output set of answers it's a probability distribution over all three. I can mix them together. And I can train a separate classifier to decide whether it's a one-hop, two-hop, or a three-hop question. So you can think of these as templates. And we can instantiate multiple templates. And because everything is differentiable, we can still train a mixture of those templates end to end. Yeah.
Wouldn't that assume that, when you're saying that R2 is encoding the second hop in some sense, right? You're trying to capture what would the second hop in general over any question be? Well, that may be different depending on the question, because you could switch it out, right? You could it might just be that you're asking it the other way around, the first.
So really what we are doing here is semantic parsing. I'm assuming given a question, there is a semantic parse, which looks something like first get X, then R1, then R2. Right. And these transformers are trying to decode, given a question, what is R1 and what is R2.
Right. I'm interested in how do they share parameters, for example.
So in this case, it was just the first n layers were shared and the last n minus m layers were unshared. It's a single transformer network with a certain number of shared layers and then a few independent layers. Yeah. So how does this do? I showed you this plot earlier with 1-hop, 2-hop, 3-hop questions, and a graph network-based approach that I described previously with just one step of retrieving and then trying to extract the answer was something like this. Recently, there was a paper at ENLP which improved on this considerably by applying that same graph network by doing multiple steps of retrieval. So you first retrieve some subgraph, try to answer the implicit question, then retrieve a second subgraph. Our approach is comparable on 1-hop, but does slightly better on 2-hop and 3-hop questions. Yeah.
So for the graph networks, are you using like a typical GCS or something?
No, so it's the heterogeneous graph network that I described in the previous section, where we have both text nodes and knowledge base nodes.
Okay.
There's actually some other algorithmic changes as well, like we constrain the propagation of embeddings in the GCN to start from a node in the question. That's a very good inductive bias because like
Not in the text, you mean?
Yeah.
Okay.
Yeah.
All right. But the propagation is similar.
Yeah, the propagation is very much like.
But you only average nearest neighbor information at each propagation step.
Yeah, exactly. Yeah. One of the design considerations that I've been focusing on a lot is efficiency of our approach. And here is some evidence for that. So here I'm comparing the queries per second to the multi-step graph network approach. And as you can see, we can be up to 10x faster for more complex questions while being more accurate. Yeah.
But was this test run given that you know it's going to be 2-hop 3-hop question?
Yeah. So in this case, I know exactly which questions are 1-hop, which are 2-hop, which are 3-hop.
To be like in a fair comparison, would you have to, because you said you won't know 1-hop, 2-hop, 3-hop, so you run 3 versions?
Yeah, so here it's a fair comparison because even the graph network approach there are 3 different models actually, 1-hop, 2-hop, and 3-hop. Okay, but let me show you a demo of a system that I've been working with. So what you can enter a question here, and this is now running on all of Wikipedia, which is about 5 million articles. And you can see that this here is a 2-hop question. What is the shape of the family of viruses containing coronavirus? And what's going on here is that it answers the first implicit question, what is the family of viruses containing coronavirus, which in this case is Coronaviridae. It then goes and finds a second passage and answers the question that those viruses are actually spherical. We can also ask other questions, like when was the university containing Information Sciences Institute established? And in this case, it first finds the answer to the first sub-question, which is University of Southern California, and then it answers that as 1880 as the date of establishment. And as you can see, this is real time. So this system is running on a single CPU server, and it's pretty fast, even though we have about 5 million Wikipedia articles that it searches the answer for. Let's try one.
Graph is pre-computed, right? So everything is pre-computed. So you are just...
Yeah, the representations are pre-computed, but the question, running the model on the question, doing the top k nearest neighbor search, those sparse matrix multiplications, that all is happening online. Yeah. So yeah, what is the population of the place where USC-ISI is located? 8,000. That's not the population of LA. That's the population of Marina del Rey, which is what's listed on Wikipedia as a place containing ISI. Okay, so I'm going to summarize the technical part of this talk. I started by talking about reading comprehension, where we are trying to answer questions given a single passage of text. I then talked about how we can actually add some knowledge graph information to those passages. And lastly, I discussed how we can do completely end-to-end reasoning over a very large corpus of text without having a retrieval step first by defining these relation following operations. And the code for most of the things that I've talked about today is available online. So now let me very quickly go over some of the other work I've done during my PhD. Today I talked mostly about single-step question answering, where you get a question and you want to produce an answer. But in some situations, it makes more sense to do it as a multi-step process and having multiple turns in the conversation. So in collaboration with Microsoft Research, I worked on a multi-step dialogue system for answering questions. Another line of work that I've explored a lot during my PhD is biomedical information extraction, where given the vast amount of scientific articles published in the medical domain, you want to extract some structured data from those articles. And most of this work was done in collaboration with the University of Pittsburgh and was driven by a brilliant undergraduate student, Chow, who I advised. And recently, I've also been working on table-to-text generation, where the goal is to produce a natural language description of a semi-structured table. And this work was done in collaboration with Google Research, and our focus really was on making those generations accurate so that they're faithful to the underlying table and don't, for example, hallucinate. Lastly, recently I've been working on interpretability and robustness of deep learning applied to NLP. So, for example, we showed that a single spelling mistake can really destroy the performance of state-of-the-art NLP models, but there are some easy fixes. So this work was driven by Danish, who's another PhD student at NTI who I've unofficially advised. So that's it about the work I've done in the past. We still have about 6 minutes. So let me quickly give you an overview of the kind of research I want to do going forward. So to set a theme, like here's one example that my friend who's doing a PhD in chemistry was telling me about. So one important problem in nanomedicine is that you want to attach drugs to these nanoparticles and deliver them to very specific sites within the body to fight cancer cells. And this paper was published a few years ago, which reviewed the literature from a decade in the field of nanomedicine and found that the actual median efficiency of delivery is only about 0.7%. This was quite a shock to people within the field because there was an impression in the field that there's a lot of progress and nanoparticle drug delivery is very successful. So as an NLP researcher, I'm interested in the question, can we automate such discoveries? Can we build systems which analyze large amounts of, say, scientific text and find inferences or patterns within that which maybe no single human has figured out? Now, this is a very, very complex task, and I'm not the first one to think about it. So, for example, DARPA had a very big program which ran for 3 years called Big Mechanism. I think there were some $45 million funding available here, where the goal was to build these causal models of very complex domains like economics and biology, and then derive new hypotheses and suggest new experiments based on the model that you have. And they sort of envisioned it as 3 steps. So you start by reading individual pieces of text and extracting information from that. Then you assemble all that information into one big causal model in that domain. And then you try to generate new hypotheses based on that model. Now, much of what I've talked about today and what sort of my future goal is the first 2 steps here, that how do we take a lot of text and build a model of the knowledge within that domain or a representation of the knowledge within that domain. So DARPA had what I like to think of as a bottom-up approach to solving this task, where they started by identifying what are the important entities, relations, events, processes that you care about. Then they read individual pieces of text to extract a small model, and then once they have these small models based on the entities that they've defined, they stitch them together into one big coherent model. Now, the problem here is that A, this is expensive to actually do all these steps, and B, there is a lot of error propagation. And what that practically means is that for any complex domain, when you try to stitch together the information in many, many different articles based on some manually defined schema, things start breaking down as you try to scale up. Instead, sort of my vision to this problem is what I like to think of as a top-down approach. So I believe that instead of identifying the model that you're interested in or identifying the concepts and the kind of the structure that you want to extract, start by identifying the relevant data. What are the questions that you want to answer? What are the interesting tasks that you would like to solve? And collect data for that. And now I'll go and ask the question, okay, what are all the different knowledge sources which I can use to solve my task? And then develop end-to-end reasoning models, which both represent the underlying knowledge and the way that and the model for solving the task that you're interested in an end-to-end manner, which is much like the works that I've described today. So let me quickly give you a small snippet of the kind of work I've already started doing in these three directions. So we're not at a stage where we can answer research questions against a biomedical scientific corpus, but can we answer research questions against a single abstract, which are actually studying the question? So we recently released a data set called PubMed QA, where we annotated these Boolean research questions and paired them with abstracts of studies which were designed specifically to answer that question. Now, already the state-of-the-art reading comprehension models that we have today break down on this type of task, which requires many different kinds of reasoning. So I'm sort of excited to see what progress can we make on this task. And once we solve this, maybe we can make the task step-by-step more complicated until we reach our eventual goal of answering open domain questions against a whole corpus. In terms of knowledge, so most of what I've described today was about factual knowledge, the kind of things you find on Wikipedia or organized into knowledge graphs. But a lot of the knowledge that we actually use is what I like to think of as implicit knowledge, which is not easy to describe in terms of entities and their relations, but it's maybe best expressed as in terms of natural language itself. So recently, language models, which given a history try to predict the next token, have become very popular in NLP. And in fact, there's an intriguing line of work which explores what kind of common sense properties do these language models encode. So I played around myself with the biggest such language model, which is OpenAI's GPT-2. And what you can do is you can give a prompt and then see how it completes that prompt. So some things make sense, like animal lovers are more likely to, and it responds with be vegetarians. That's common sense. But then sometimes just changing that query to a different format, like people who love animals are more likely to produce as nonsense, like be atheists. And it's also very bad on factual knowledge. So if you ask it, the light bulb was invented by, it says, Nikola Tesla. And this is really exactly the kind of thing which we can tackle with the approaches that I described today. So that's sort of one thing that I'm interested in. How do we combine the methods that I've discussed today with these intriguing new repositories of knowledge in terms of language models? And lastly, reasoning. So what I described today was binary relation following, which we are interested in facts like these. But a lot of knowledge is actually n-ary in terms of n-ary relations. So maybe you have a subject and an object, but you also have a start time and an end time of the relationship. So currently I'm working on generalizing the methods I presented today to handle higher order facts like these, and also look at temporal reasoning. So can you answer questions like who was president after Nixon and before Obama, for example? And lastly, further ahead, I'm also interested in counterfactual reasoning, which is really a core component of scientific understanding scientific articles. Thank you.
So your entity linking links the spans of text to the entities in the knowledge graph.
Yeah.
Nothing is linked to the edges.
Yeah, no.
Is there value on trying to somehow do that too?
Absolutely. So the idea here is that it's okay to have redundancy of information, right? Like if I have an edge in my knowledge base, it's okay to have the same relation expressed 15 more times in the text. But what we really want to do is make sure that if there is some information relevant to diabetes in my text, I want to connect it to that piece, which is why we really focused on entity linking to start with. In the most extreme case, you can actually get rid of the edges in the knowledge base completely. And in fact, the last part of the talk, I did that. I did not assume a KB plus text setting. I just assumed we identified entities and we don't have any information about them. So in general, I believe that keeping things in their raw format is maybe good, as long as you have good algorithms for making sense of that raw format.
Yeah, but in a sense, you're throwing away the relations of the knowledge base, and then the question.
No, so you can add them, and as I've shown you, it absolutely makes sense to add them, because sometimes if a question can be directly answered by looking up a fact in your knowledge base, that's a much more robust system in general. So yeah, whatever structured data you have, you should try to add it. Yeah.
I'm interested in the representation of the relationship.
Yeah.
You follow the relationship. So what will happen in this case? For example, like one author a paper, this is relationship, and the paper is authored by like the inverse relationship.
Yeah.
So will your representation recover itself if it goes a loop like this kind of inverse relationship?
That's a great question, actually. And some of the questions we had suffered from that problem. So if you have a question like which other movies are directed by the director of Pulp Fiction, you go from Pulp Fiction to Quentin Tarantino, and then you come back, Pulp Fiction is already in that set, and you want to somehow remove that. So for now, we handle it in a hacky way. We just take a difference of the operation you get after two steps with the set of entities that you started with. But that's still sort of a more, like, how do you understand that you want to remove certain entities from the set that you ended up with? That's still an open question. Yeah.
Second question is like, how is the, if you have like a description, it's a two-hop, and who defines the order of those two relations to follow? So does the two relationships commutative in
So the question defines that. The natural language question implicitly defines an order between those relations. If I ask you where is the company which manufactured Vogelibos headquartered, there's already an order defined there in the natural language. That first you want to find the manufacturer, and then you want to find the headquarters. The other way around is incorrect.
Another way doesn't.
That order is derived from the natural language question itself.
Okay, thanks.
Okay.
Well, online. I'm going to check the questions on.
Oh, are there any questions remotely?
No questions for me.
We can hear you, but the volume was low, so if you can be louder. Liz, are you asking a question?
I was just saying nothing for me. Thank you for the talk.
Okay, cool. Yeah, then let's thank our speaker again. Thanks, everyone. Cool. Pedro.